at Google, and my work has been mainly around application modernization and emerging technologies. I am an active conference speaker, and generally, I have been speaking around Kubernetes, platform, distributed systems, and DevOps SRE landscapes. Uh, as I mentioned, today's session is going to focus on GKE Inference Gateway. This is a recent addition to the GKE stack. And in case you have any questions, feel free to chime in or probably raise your hand or write on the chat box. Siddhi will be helping us moderate the session. If we see a lot of questions coming through, we'll be taking those questions towards the end of the session in a dedicated Q&A. The length of the session is roughly going to be 30 to 40 minutes. And just a disclaimer that we are going to discuss about some of the stuff which might give you an impression that we are talking about performance gains, etc. The intent of this particular session is not to advertise slash evangelize or sell any specific performance gain related functionalities or products. It's just for understanding what exactly happens when we are serving workloads on Kubernetes and how exactly they look like when we have them served through Kubernetes engine, what all features we have. So this is more of an awareness and knowledge augmentation session than selling anything. So don't take any of the views presented here coming from Google, take them from coming from my experience. So it's all personal stuff that I'm going to talk about. So let's get started. We need to understand that these days a lot of hype is there around AI. A lot of people are investing in research as well. So some people are really thinking it from a perspective that AI is going to change a lot of things, and some of the people are just trying to get close to the hype and they are trying out new kind of things. Ultimately, what happens is that for the people who are really interested in serving AI workloads, they are trying to find how we can have cost optimization done for serving AI workloads, how we can have performance gains, how we can do some sort of intelligent routing so that we can have effectively we can have effective inferencing or serving of the AI workloads done, etc. So this is where we see that the trends are changing. AI workloads are no longer or cannot be treated as workloads like regular web applications. So we need more or less this particular thing or the first objective to be met as part of the AI serving model from our side, which is self-hosting. Because you see that when you go ahead and try to go over some platform as service or SaaS related AI serving functionalities or products that are there, they generally tend to cost more when you try to get more traffic or more load. This is where you think of probably having some self-hosted generative models hosted on, let's say, Kubernetes or virtual machines. And that is where we do see a need to have some sort of standardization, some sort of let's say extension processor kind of thing like we have in other gateways like Envoy to be there, which can give us an interface through which we can have proper hosting of the models done in a standardized manner. The second thing is that the AI workloads these days are going to have a lot of fresh requirements also pouring in. Some of the common requirements that we have seen in the past include latency sensitivity. So people are generally looking for more real-time experience with workloads. So you see that when you are interfacing with the chatbot, your expectation is that your response gets served as soon as possible or in a jiffy, as in when you type in some prompt, you are expecting the response from the chatbot. However, when we come to, let's say, deep thinking related uh, use cases, in that case, you are not really bothered much about latency sensitivity. You are more bothered more about the context length, and also if you can have good information served in form of output or like detailed information served in form of output. So latency sensitivity is something that we have to generally deal with. Also, context window length is something that we need to deal with. So this is completely, I would say, fresh from a perspective. If we were to consider it as an application developer, a regular web application developer getting into AI model serving. Then we do have some advanced load balancing requirements. Generally, you see that you open some host application or desktop application wherein you have to interact with the LLMs. Sometimes you see that you provide a big prompt and ultimately you see that the model was not able to serve, or there was an error that, okay, we were not able to produce results. And ultimately you have to wait for some time and reattempt submitting your prompt. And after a couple of attempts, you see the response coming, but you have to wait. And until then, you keep on seeing errors. Then there is something called as model aware routing or model serving priority. So generally, in industrial applications or enterprise applications, you won't be relying on just one single model. You ideally would be looking at a bunch of models. So you would want model, let's say DeepSeek for doing some recommender stuff. You would want Gemma to do some text-based stuff. You would want some other image-specific model to do some image manipulation, or let's say captioning of image, etc. So this is where you could be having the same endpoint, but that endpoint could be having different behavior getting exhibited based on the models that are getting selected. Sometimes it could be payload or body specific, wherein you could be just focusing on one modality, let's say text only, but you could be saying that, okay, I want the response from Gemini, and I want the response from Claude, and I want the response from some other model. And probably the model criteria should be that based on some specific identifier, like the person requesting or the user agent requesting for inference, or let's say the company which they belong to, or the region which they belong to, or any kind of payload information or query parameter field could be there, based on which you want to do some payload based or body based routing. So this is where it could either be a model based routing, or a body based routing, or a model aware routing. And it can be dynamic as well, like in on the fly when the request has been submitted, then the decision gets taken as to which model needs to serve. Because sometimes it could happen that your model behind the scenes has got the tokens exhausted. It has probably hit the quota that it was defined with, and now you cannot really have the users suffer because of the quota getting exhausted. So you have a fallback model on which you want to go, and you want to serve from that particular model. So such kind of things generally are part of body aware routing, or model payload based routing, or let's say tokenization that you can enforce for LLMs, etc. And based on that, you want to do routing. So there are some capabilities which can be dealt with via Kubernetes only, based on the Kubernetes extension model or the inference extension model that we are going to talk about today. Some of the capabilities are better fit for service by something called as model as a service provider. This is a new again term that has come, model as a service provider. So you would have heard about management solutions or API gateway management solutions like Apigee, like LLM Lite, or like Envoy AI Gateway, Kong, and all. So this is where these model as a service providers can complement what Kubernetes is serving, and can help us with things like LLM tokenization, aware routing, or monetization, or analytics insights, etc. So we are going to touch briefly upon those things as well towards the end of the session. Then comes A/B testing, canary testing, any kind of testing that you would want to do. So this is where you are deploying a model, you want to deploy a newer version of the model after you have incorporated the feedback. This is where the A/B testing thing comes into picture, and you want to do some traffic splitting. It could be percentage based, it could be weight based, it could be based on some other factors. So this is where you already see that, okay, this has some commonality with the regular ingress or the gateway features that we were using with Kubernetes, but now it has something more to do with respect to models specifically, because it is no longer a normal application. It has stuff related to the underlying resources getting utilized, which are no longer just CPU and memory. We have GPUs, we have TPUs, we have some other tangible resources as well. Ultimately, we come to a point wherein a lot of people these days who are creating self-hosted generative models are under resource crunch. Many times it happens that you have single GPU which is on a host, and that GPU needs to be shared by multiple tenants. Now, sharing is something which by default in GPUs is not possible, because GPUs don't have a concept of vGPUs configured by default. So you either have to do hardware slicing that can give you isolation in terms of fault tolerance and memory. This is something that you can do using multi-instance GPU from NVIDIA, or you want to go with something basic like time slicing or MPS. These are again things which could help you realize some sort of kind of sharing of GPU, wherein at the same point of time you won't be sharing the same GPU if it's software based. You rather would be getting access to GPUs in turns. So it's more of like time slicing or multi-process access, etc., which is sliced in some manner. And when you are doing time slicing, the context window switch is so much that you generally don't get the desired performance. So this is where there are some techniques that you should be using from serving perspective, which can really help you regardless of which time, which GPU sharing technique you are going with. And for people who are interested in further checking on the concept of vGPUs, there is a talk from me which is called Declarative Device Virtualization that covers a specific tool called HAMI, wherein I show how you can have a software level configuration which can help you access GPUs in a multi-tenant fashion without having to get into context switching challenges, etc. So that stuff we are not going to focus much upon today, but I'm just referencing that it's called Declarative Device Virtualization with HAMI. It should be on YouTube as well. And we generally see that GPUs and TPUs are these days getting considered as the go-to accelerators. People really don't understand when to use GPU, when to use TPU, when to use CPU. So I'm not sure what kind of experience this particular audience has, but for people who have been using precision-focused arithmetic operations, for those people, generally going with GPUs would be better than TPUs. For people who have any specific, let's say, TensorFlow operation related dependency, a lot of TensorFlow operations are not supported with TPUs, so you will need to go with GPUs in that case. If you have any kind of linear algebra programs which are getting executed in the main loop, then also TPUs won't be fit and you will need to go with GPUs. Where TPUs would make sense would be like long running training cycles that are there, which probably are running multi-days or even weeks, or you have large batches of training. That is where TPUs can help. But generally, for complex logic, wherein you have precision arithmetic, or you have operations in the main loop, or you have dependencies on libraries like PyTorch or JAX operations, which are very complicated, those will generally require GPUs. So this is where GPU, TPU choice, when to use which one, all of those things are also something which are popping up as part of the inference journey. And hence, you should be having control based on some parameters, or based on some body related understanding, or based on the model serving dynamics. You should be able to dynamically route the request to TPUs or GPUs without having for you to jump in and decide when to have such kind of thing, or without having to hard code your backend pool which is serving the pods. Then we get into this unified management for traffic policy enforcement and observability. This is where we do see that these days there is certainly a requirement to have some sort of traffic management done, not just at the level of load balancers, but also at the cluster level. So people who are using things like service meshes or multi-cluster ingress, or who have any kind of disaster recovery or high availability use cases that span multiple data centers. This is where a unified management for traffic is required. Also, we should not really ignore the security related aspect. So this is where, if you want to enforce any policies, or you want to have some specific nature exhibited from security perspective, you should be looking for something which can be enforced at a blanket level, rather than doing in a point manner, cluster by cluster or service by service. And ultimately, whatever we are talking about is something which will not be possible unless we have an end-to-end visibility, or any kind of telemetry for. So that's where the observability portion comes into picture. So these are some of the top requirements which made us think about, okay, why not have some standardized solution and interface which can go about having self-hosting of the generative models done via Kubernetes, because Kubernetes is getting very popular. You have a lot of these model as service providers and gateways, Nginx, K Gateway, and whatnot coming into picture, and with MCP and A2A and A2P, etc., all coming into picture, this particular landscape is further flourishing. So with this, we get into the main, I would say, high-level resource model where the different personas fit in. So you need to understand that generally, and I'm assuming that most of the people here are already aware of the Kubernetes Gateway API, the vanilla one, not the inference one. If not, then you can just type in chat and I can give you a quick overview of the same. But this is essentially for having load balancing capabilities for Kubernetes introduced so that you can have a layer 7 load balancing. You can intercept the payload and you can take intelligent decisions based on what is there in the payload or what is there in the request. This is a successor of the native ingress that used to be there in Kubernetes, and both ingress and gateway can be used on the same cluster when you are doing, let's say, migration or for different use cases for different tenants. But generally, gateway is considered as a successor for ingress unless you have very specific use case wherein your dependency is on the ingress provider for which you don't have a gateway class. So gateways generally have a concept of classes, and with Google Kubernetes Engine, we have defined classes for external exposure, global exposure, regional exposure, internal exposure, and so on. So gateway and HTTP route together essentially help you define, okay, my request is coming, it matches so and so path, it has some headers, it has some query parameters, or it has some layer 7 behavior. According to the behavior, according to the parameters, according to, let's say, annotations, I want to route the traffic to some specific backend. Now, traditionally, if we talk about the vanilla serving model, that is where the backend used to be a service. So this service is a Kubernetes service, the regular Kubernetes service that you are just exposing in L7 capacity like you used to do in Ingress. With this GKE, with this Kubernetes inference extension coming into picture, you have somewhat equivalent of service coming, though it is not having the network related intelligence, which is called inference pool. So inference pool, if you were to consider, inference pool is nothing but a pool of pods you can consider, or model servers or replicas you can consider, which have the same configuration, same compute type. They are homogeneous. Basically, there's no heterogeneous configuration out there. They have the same base language model, and also the model server dynamics are the same, and they are powered by either GPU or TPU or CPU depending on what the family looks like. And ultimately, this inference pool is what is a new resource which has got added as part of the inference extension for the Kubernetes gateway. And this primarily focuses on the inference use cases along with some routing extensions, like you want to have routing done based on some priority. Let's say two requests, concurrent requests are coming, and you want the gateway to decide which request should be served first because of some urgency or the priority that you have defined. So that is what you can define using something called as inference objective. So these are two custom resources. So CRDs for the same have got introduced as part of the GKE inference gateway, or like if you want to talk about open source, then it's called Kubernetes Gateway Inference Extension. So these two are the custom resources that have got introduced, and there are different personas now to handle these. So one is the inference platform owner persona, and one is the inference workload persona. Inference platform owner will be defining how the inference pool would look like. This is where it will be specifying the pool spec related information, what the target backend services would be, what the target port would be, etc. We'll shortly see an example of this as well in action. And the inference objective, as of now, can specify the priority, but in future there are some targets for the open source project to even have SLOs, etc. considered. So that is where it has a good future from a serving perspective. So this is how an inference pool looks like. You define it like any other Kubernetes resource. And this is the vanilla Kubernetes example that I'm giving, not the GKE specific one. Here you are specifying the name of the inference pool, and then you are specifying the target port. So what exactly happens is that this inference pool gets created. This inference pool is essentially going to target pods of an application that has this particular label selector. And if this application exists, then for that particular application, port 8000 is going to be used as the target port for routing the traffic. Ultimately, the decision that gets taken from with respect to routing is essentially based on another resource which is called endpoint picker, and that endpoint picker or EPP resource is something which gets identified by the EPP service defined here, which should be exposed on some specific port. And there are failure mode related metadata configurations also supplied. Like, what happens if the endpoint picker itself is not able to identify which backend or endpoint slice this particular request should be going to? Then in that case, the endpoint provider will return a 429, and your request will be dropped. However, if the endpoint picker essentially gives you that, okay, this is the pod which your request should be getting routed to, and we will see what all those factors are which will be influencing the EPP's decision shortly. Let's assume endpoint picker is a service which is running, which just tells you, okay, out of these pods, this particular pod looks to be free right now. Let's route the request there. Or this particular pod seems to have the required model. I'll serve it from there. Such kind of decisions get taken from EPP layer. And there is another component, which is the BBR component, or body-based routing component, that sits, that works in conjunction after the request has been received at the gateway with EPP. The body-based routing decision controller decides if there are any body-specific routing logic or routing decisions that need to be taken, and ultimately then your inference pool gets selected to which the request needs to get routed, and a specific pod of that needs to serve the request also gets identified. So overall, like, if I have to sum it up from inference pool perspective, and probably there is some issue with the delay with the streaming, so I think the images are getting uh, loaded in a delayed manner. But if you have to do kind of a comparison, this is the Venn diagram showing the common area. So between inference pool and service, the commonality is that you are able to have pod selectors and port configuration specified for the targets that you want to have for your model serving. However, there are differences, like inference pool is not really meant for doing network operations. Like, it doesn't have the DNS records, it doesn't have the load balancing capabilities in its own. It is just meant for having the identified pods routed towards, and then ultimately it's something which is very specific for inference use cases. It's not really meant for any protocol specific lower level operations, nor it is meant to be used with any CNI or container network interface plugins, etc. Okay, so let's get into the entity relationship at a high level as to how it looks like. So we are now going to understand how many backend services or let's say pods can be reached out from the inference pool, how, let's say, backend references interact with the inference pool, what's the relationship between an inference pool and inference objective, and such kind of things. So let's assume you have a gateway which has an HTTP route with 3 backend references specified. There could have been multiple HTTP routes, but for brevity purposes, I have kept it like this. And specifically, you are having one backend reference point to the inference pool. Inference pool essentially has this endpoint picker bundled along with it. So there is a one-on-one relationship for this particular inference pool and this particular inference pool. That's why I have labeled it as EPP2 and EPP1 respectively. And you see that there are multiple backend references that could be pointing to the same inference pool. This could be because probably we are doing some sort of transition, or we are doing some maintenance activity, and we want to have this particular backend reference get 90% of traffic and this get 10% traffic, or probably this backend reference has got some other annotation or label, or probably some metadata that needs to be floated, which actually was met as part of the HTTP route configuration. And that's why we are also routing it to the same inference pool, because ultimately the model that needs to be served, the configuration that needs to be served, and the compute classes, etc., that are there, those match what are needed for inference pool 1 as well. So basically, inference pool backend remains the same for the 2 backend references, but the backend references related metadata and configurations could be different. Then you can actually have different inference objectives attached to the inference pool. So like here we are having 2. So objective 1 is actually serving different set of requests. Probably it has a different priority defined, and then objective X has a different priority defined. But ultimately, if you are passing a header in your request which explicitly is defining which particular priority I need to go with, like there are specific headers also that you can pass on from the upstream, then in that case you will have these 2 inference objectives work well with the inference pool 1. However, inference objective X won't be applicable to inference pool 2 because there is no attachment defined. So there is a attachment that you need to define for any kind of behavior that you are defining through the inference objective. For now, you can define priority of the request to be served, but in future there are plans in open source to have sort of SLOs, etc. And ultimately, this EPP is able to monitor the metrics as well as to how much load is there, what kind of low rank adaptation models have been loaded, or whether it's the base layer in the model server or replica that is serving. So this is where your whole understanding of how model serving is happening comes into picture. It actually should be traced back from very much the model server to the endpoint picker to the inference pool, and then you have the decisions getting taken basically. So coming to the high level request flow, this is where the vanilla or open source Kubernetes gateway with inference extension enabled works like. So it has the client request coming on this endpoint, let's say completions. Then this request goes to the body based routing and EPP for kind of doing selection. Now, basically, you need to understand that uh, when a model server has to serve the request, it really needs to have some GPU resources free so that you can have some computation done for GPU. Also, it should be able to have some sort of the queue should be free. Basically, it should not be that there are a lot of requests already in queue for that particular model server, and you are going to that model server only instead of the one which is actually free. So such kind of things you have to focus on. This is where the endpoint selection and the body based routing concepts come into picture. These services essentially help us understand which model server needs to be routed to, and ultimately then Kubernetes gateway takes the decision that, okay, based on the information that I have received, this is my pod or model server that I need to route to. And this is how the GKE version looks like, which has a bunch of other additional things. So you have end-to-end observability getting captured. So there is a custom resource called pod monitoring that we will see shortly, that is deployed as part of the inference gateway solution, let's say. And ultimately, you are able to have all the observability related metrics, etc., flow to your Google Cloud Observability. Additionally, there is something called as Model Armor. So Model Armor provides with content filtering and AI security and model safety. So this is where, let's say, you have to get protection against jailbreaking or prompt injections, or you want to anonymize anything or sanitize your prompts, be them coming in form of inputs, or the prompt responses that have been generated from the backend also needs to be sanitized or need to be checked that, okay, whether you are sharing any PII data or any identifiable information. All those checks can actually be done using Model Armor. So there is a direct plugin here wherein you can have security related extensions, and likewise there are GKE extension processor or service extensions that you can write to do some custom logic also with respect to how you want to serve. So these are some additional add-ons on top of the open source stuff. And then there are a lot of other I would say enhancements that recently got launched, like about 7-8 days back only, when there was this KubeCon Atlanta event. There were a bunch of new features, prefix aware caching, etc., and some other optimizations that were surfaced as part of the launch. So now let's see how GK Inference Gateway features could really help us for solving our issues that we saw in the first slide, or the changing trends that we saw. So we actually have some supported metrics getting reported, and EPP, as I mentioned, is the one which is helping us retrieve some of the metrics from the model servers or the replicas. So KV cache hits are what we are getting. So for people who are new again to this AI serving and all, I'll quickly explain what KV cache exactly means. KV, as you might have already gauged, it stands for key value, but then what exactly the key value is for. So let's say when you are dealing with LLMs, you are supplying a prompt and you are expecting some response. The response, let's say, should be the quick brown fox jumps something, let's say a random sentence. Basically, each of the words that are getting generated, or the tokens that are there, let's say the quick, brown, fox, all these things that are getting generated, what the next word should be also needs to be kind of retrieved from the semantic information that is there as part of the response that is getting generated. So KV cache hits or KV cache utilization behind the scenes, it has three vectors, essentially like one vector called Q vector, and then there are two matrices K and V. These are getting maintained, which essentially help us with the next term, which relates to the semantic of what exactly should be presented as the next term. So KV cache hit, when we say, so key and value that get stored are nothing but some vector or matrix representations. These representations have something related to the context that we are looking for in form of the next token that should be outputted. We don't have to really go to the mathematical formulas, etc., but you can understand that when we are generating the next word for a sentence, like we generated the and then we generated quick, after we have to generate after this we have to generate the third word. Third word will need to really process the first two words again and their semantic relationship before suggesting the actual third word itself. So this is where for every such next token generation that needs to happen, you have to process whole of the stuff again. The beauty of the mathematics behind the scenes is that the computation that we are having doesn't really change. So the value of K and V for every term that is getting generated remains the same. So we actually can cache the K and V values rather than regenerating and reprocessing everything. That's why you see that sometimes some of the LLMs provide responses at a much quicker pace than some other LLMs. Some LLMs are just generating thinking, but some LLMs are just writing the output at a very fast pace. This is because those LLMs which are producing the fast outputs are using something called as KV cache utilization, or cache aware routing also. So that's where all the speed and optimization is coming. Like we will see this in action shortly in the demo, but we won't get into the mathematical details of this. You can just assume that there is some sort of vector and matrix operation that is going behind the scenes. GPU, TPU utilization also we get to see, and then request queue length as to how many requests are there waiting for inferencing are also reported. Then there is something called as prefix cache aware routing. This prefix cache aware routing, you can just assume that, okay, if your prompt matches the longest prefix out there in some model server which already has KV cache done, which one has the most matching prefix is going to be picked next, because that way you won't really be required to do a lot of computations. You will be picking up the responses from the previous set of computations that were cached. So this is where prefix cache aware routing essentially is for picking up the node which already has some computation done, so that your response generation can be made quick. Dynamic LoRA, so this is low rank adaptation. This is where you have some base model, and then that base model is fine for serving a lot of requirements, but then there are some minor tweaks or opinionated, let's say, responses that you want to give, for which you train or fine tune some additional adapters and you deploy on the base model. So GKE Inference Gateway is able to understand through the EPP the metrics that it is getting and the active map of LoRA adapters that are there it is getting from the underlying processing that it is doing. It is able to see which nodes have some specific model adapter getting used, or it was used in the previous set of requests, so that you don't have to reload the model adapter on any new node. Rather, you can route the traffic to a node which already loaded the model adapter, and then you can have quick inferencing done again. So it's not just about talking on how the model inference server would work, how quantization, pruning, etc. will work. We have to think about these things as well, as to how from load balancing perspective we can do intelligent load balancing so that we can have quick serving of the models done. Then we have inference oriented optimized auto scaling. So HPA profiles are there which can reference now custom metrics and model server metrics. So this is pretty much, I would say, a traditional thing using custom metrics, but it has been implemented with model server metrics as the metric source for inferencing. So this is where you can have the pods auto scale based on the model server metrics. Body-based routing, model safety, and inference observability we have already touched upon. So this is how it could look like. The regular gateway, if we go with traditional one without the inference section, you can have HTTP routing to a service, but then we can have inference pool also considered when we are talking about the actual inference use cases. So this is where we see that this particular gateway has the hostname example.com, and this is routing to slash completions. Now, slash completion can actually get two models based on the query, let's say parameters or the model body, the request body that is there for the model inference request that we are making. The model name could be a chatbot model or could be a recommender. Now, based on chatbot recommender, what this inference model and EPP would do in behind the scenes, there could be even priority specified here, which I have not reflected. They will be routing to the correct inference pool. So for inference pool, that has to relate to chatbot. The pool is powered by Gemma model, whereas the one which has a recommender, that is, let's say, serving DeepSeek. So this is where you can actually have the very same path, but using different models, route traffic to different backends altogether. There are other things also that you would have seen in GKE if you would have been, if you are already a GKE user, like node auto provisioner, compute classes, etc. Those kind of things also can be made to work alongside in a complementary fashion with what all I am discussing. But today our focus is not on the capacity side of things, rather load balancing side of things. So we won't deviate that much. But for people who are really interested, you should go ahead and see the HPA, VPA, cluster autoscaler, node auto provisioner, and compute classes for GKE. Those aspects are also going to help you do a lot of intelligent serving for your models. Ultimately, what we are able to do with what all I have discussed so far is that if you see the traditional round robin serving, which is without GK Inference Gateway with a regular load balancer will be using something like a round robin algorithm or some specific algorithm, but not something intelligent to gauge the model requirements and do routing accordingly. So this is where you see that it keeps on hitting, let's say, a node too often, that the pending requests in the queue grow, like shown here, and likewise the KV cache utilization also grows. However, this particular node is free, and this could have served the request, but because the load balancer was not aware of this particular node's properties or the real time, let's say, behavior that it is exhibiting, it ended up doing the round robin thing and ended up on this particular thing. Now, what happens really is when the queue lag starts building up, sometimes the lag is so much that many of the requests will get dropped and will be returned as 429. Sometimes it happens that the underlying server itself will be running out of GPU, and hence there will be memory kill. So there will be a lot of issues if you go with this traditional routing model. However, when you get to the GK Inference Gateway, because you have prefix cache aware routing, because you are considering the KV cache utilization metrics, because you have LoRa adapter related intelligent routing, and because of all the other great features that the Gateway API has to offer, in addition to what Kubernetes can offer, you are essentially able to route the traffic to the one which is least utilized. So now you actually get to efficient utilization of GPUs, and you are not even keeping your nodes idle. So this is where it's cost optimization, and we have seen in scaled use cases where enterprises are using GPUs extensively, that when they switch to such kind of a model wherein such intelligent routing is happening, they are able to accommodate more requests with the same infrastructure rather than having to scale pods. Because generally what you would do is, in the traditional routing, you will see that there is bottleneck without doing, let's say, deep study as to what exactly is becoming bottleneck. Most of the people will go ahead and shoot up a new replica or a pod, or probably bump the HPA count to, let's say, 10. They will think that, okay, HPA threshold is something which is becoming bottleneck, but the actual thing is that the bottleneck is the load balancing itself, not the HPA. And for that, you need to do a lower level study. However, in this particular use case, your HPA also can respect the thresholds that you are setting on the capacity for your pods, etc. So this is where a fair scheduling can happen, and this is where you will see a lot of, I would say, benefit coming when it comes to routing. So let's start with something called as GK Inference Quick Start. So this is a utility which is available, which can give you recommendations on what exactly could be fit as a model for you. So here you see that you have a G Cloud Alpha Container AI Recommender API. Now this is a CLI that is available that you can use, which is depending on your model requirements, telling you which model has what, let's say, normalized time for first like TTFT or NTPOT, etc. All these output time or input time or time to first token related metrics are getting shown to you by model. So this is where you can actually go ahead, use this CLI for getting an understanding as to which model will suit your SLA requirements, etc., your serving requirements, how the performance would look like. And ultimately, through the CLI, you can even generate the manifest like I generated, and you can apply. So you can see that I have got the kubectl outputs now for the manifest that got applied. So I'm getting the pods, I'm getting the service, and I'm actually getting all the additional resources like HPA, etc. And now, once the pod status shows as ready, which I think should be showing now, we are ready to serve our workload through this particular model. So this GKE Inference Quick Start is a very good CLI tool. It is also available on the UI if you are using the GKE console for you to go ahead and pick from the list of models. The models will show the performance insights. They will show how in the benchmarking they performed, and you can see how much is the time to first token, how much is the normalized time to the output token, how much it is taking for it to serve, let's say, heavy under heavy conditions, etc. All those things can be done. So this recommender CLI is really a must-have if you are just getting started and you are not that experienced in choosing your specific models. Then we will see another demo. This is where we are having the inference gateway deployed, and I have done a kubectl get on the gateway just to show this particular gateway has 6 model replicas that I'm routing to, and basically you can see on the left hand side the KV cache utilization is for a regular load balancer which is doing round robin, and on the right hand side of the divider you see the graph wherein the KV cache utilization is looking steady. So now for these 6 model replicas, I can see that there is a lot of I would say unequal utilization of KV cache on the left hand side, but on the right hand side all the nodes are essentially having almost the same KV cache utilization. You can see the graph is pretty clean on the right hand side. Now because of this, if you look down, the average queue size on the left hand side has gone with some spikes. So you see that because some of the nodes are getting overwhelmed with the request because it's a round robin thing that we were seeing in the diagram, the average queue size of the load balancer based routing is shooting up, and hence that just means that there will be delays in serving the request. So I'll just move down and I'll show you how it shows up. So you see the average queue size. So there is no queuing actually happening when we are doing KV cache in this particular demo. So we had like 300 QPS done, and we prepared the load and we had this experiment done. And this is where you can see that the queue size essentially has gone. So there is no queuing actually happening, because of which the time to first token also will be pretty quick. So you can see that all these time to first token latencies, etc., are pretty less as compared to the load balancer option. So right side is more optimized for serving inference use cases than the left hand side. Right side is what is getting powered through GKE Inference Gateway. This is just one example. There are multiple that you can go ahead and try out, and likewise the time per output token and the NTPOT related details also, you can see it's much better when it gets to the GKE Inference Gateway. Uh, let's get to the next slide. So we have talked about the GK Inference Gateway, but I'm towards the end of this particular session. I want to highlight on some of the other stack optimizations also that you can do beyond GKE. So this is where we will get to a 5-layer framework. This is like the edge gateway layer, the first layer, let's say, which is towards the uh, furthermost point when the client hits. Then the serving platform, the model runtime ecosystem, the model itself, and the hardware. So here, before GKE gateway as well, you can have some sort of API gateway management solution like Apigee deployed. I'll show you one example as to how it is helping with semantic caching for use cases wherein semantic caching could be useful. You could enforce security. You can have CDN, web application firewall, reCAPTCHA checks, bot detection, and whatnot. All these done at the load balancing layer. Then you have an option. You don't have to necessarily use the GKE Inference Gateway. You can go with Inference Gateway, or you can go with serverless, or you can go with, let's say, Ray distributed training on GKE, etc., or Ray serving, inferencing, etc. All those things can be treated as your serving platform behind this edge gateway stack. Once you have decided your serving platform, then you can decide what your model runtime would be, whether it will be VLLM, whether it will be, let's say, Triton or TOTServe. You can really have those kind of things also tuned as part of the gateway. So if you want to do with regular Kubernetes inference gateway, or the extension, you want to switch from, let's say, VLLM to Triton, then there is a Helm chart in which you will need to supply your preference for the model serving layer, and you can switch from VLLM to Triton. But there is something called as LLMD related project also that is now in open source, which you should check out, which I'll not be able to discuss as part of this particular session. That is for high scale, high performance inferencing, wherein you can have a lot of other factors also taken into consideration for the model runtime and model serving layer. That's called LLMD. And this model layer, if you are not really serving self-hosted models, or even if your self-hosted models are backed by storage or Vertex, let's say, you can really decide how you want to have the storage for the same defined. So sometimes you can do fuse operations using Google Cloud Storage Fuse, wherein you can have mounting on your pod done for any kind of, let's say, checkpointing requirements, etc. Sometimes you have to do a lot of management in terms of common data across different pods. Then in that case, there are other storage mediums also available, like hyperdisk ML, or there is Lustre now available for POSIX compliant related stuff. So all those things you can get into. These are like some, I would say, stack related terms and features, or product areas that I am talking about, which can be your go-to things for exploration after this particular talk, if you really understand GK Inference Gateway. And then ultimately the hardware layer, as I mentioned towards the beginning, you should be checking out NVIDIA multi-instance GPU. If you have already checked that out and you see that hardware driver related changes could be cumbersome, or if you think like you want more of software control, you can check out the HAMI declarative device plugin, or probably wait for some time. There will be a dynamic resource allocator related resource also, which HAMI is coming with. So it will pretty much look like the persistent volume claims that you make. You can make claims for GPU as well through DRA. That is something which is in open source. I don't have the ATA for the same. The maintainers for the same can be checked out with for the roadmap for the same. So go to the HAMI project, check out the DRA stuff, and you can open bugs and issues there. So ultimately, I'll now show you an example wherein Apigee is also in the loop here. So I'm just going to make a request from this chatbot that you see. So I'm going to ask questions which are semantically co-located, let's say. So I have asked the first question, why is the sky blue? You will see on the right-hand side that the debugging session will have the request registered. It is taking 2806 milliseconds. Now I'll just go ahead and I'll have a semantically similar query made. Sky seems to be blue. Why? And now you will see that already the caching would have happened in the background, and you see the time reduced from 2800 millisecond to 232 milliseconds. So that's a very big gain in terms of what you are serving. So you actually did not have to go to even GKE. This particular stuff was served from a semantic cache or vector store, and this was purely done via the API gateway management feature. And in this particular specific example, we were using Apigee as our API management solution. So with this, these are some of the additional resources that you can go through. I'll be having the deck shared, so you can copy these QR codes, or you can just hit the links from the deck. And with this, I'll be concluding the session, and I'll be open for question and answers for people who want to participate in a quick survey as to how this talk went, or whether you learned anything useful, or you have any feedback. Feel free to fill in the perception survey. For people who want to try out Vertex AI Studio, there is a free trial available. Feel free to scan this particular QR code. And for people who want to connect with me on Twitter or LinkedIn, this is the QR code. This is essentially having links to both of my social coordinates. Thanks again, everyone, and I'm open for questions. We do have 5 minutes. If you have any questions, feel free to even unmute yourself or type in the chat box, whatever is convenient for you. Or else, like if you feel like checking offline over LinkedIn or Twitter, that is also fine. Thanks, Adrian. Siddhi, you have any concluding message?
Yeah, sure. Yeah, sure. So I was just waiting for attendees to drop any questions or confusions if they got.
Hmm.
So let's just wait for a few minutes.
Hmm.
Yeah, and then we can wrap up our session.
Sure thing. Yeah.
Yeah. So, folks, in meantime, if you see at your screen, so the first scanner, it says that's a quick perception survey. Go ahead and scan it. Let us know how was our session, what improvements or what changes can be done in our future or upcoming sessions. And also for the next scanner, if you see that's a free trial for the Vertex AI Studio. Go ahead and scan it. You're gonna have fun trying all the different, all the different factors of all Google Cloud and the rest of the last scanner. If you see, that's with the great DevTalks. So just scan it and get connect.
Okay.
Studio.
Siddhi, can you share the link to free AI Studio registration?
Yeah, sure. Just give me a moment, Marcus.
And meanwhile, I'll show you something really interesting so that you get something outside what we discussed in form of self-service labs. So there is something called a GKE AI Labs. This is a site for which I'll be putting in the link. There are self-service labs that are available for different kind of categories, and there are even things like agent blueprints and notebooks available. So for the notebooks, like you can really go ahead and see things like how to fine tune Gemma 3 on some specific machine type, and do a layer 4 kind of pooling, etc. You can do GPU TPU experiments. You can even play with job schedulers. If you are into high performance computing, have worked with Slurm, this is also one good lab that you can go with. If you are looking for some orchestration, there are even Ray or a dynamic workload scheduler related links. These are all self-service labs that you can go with. Likewise, agent related demos, etc., are also available. There are blueprints that are available that you can go with, like how to use a RAG in this particular use case, which is powered by the GKE architecture. Pretty good self-help guides are there. So I would really encourage, for people who are getting started or even people who are tenured, this is a good place to try out things. These are really good labs available. Okay.